Hi everyone. In last session, we have discussed about isomerism, introduction, and about chain isomerism. Today, we will discuss about position isomerism. Second one, it is instructional isomerism. Position isomerism means compounds, with same molecular formula, same MF. MF means molecular formula and differ differ the position of differ in the position of multiple bonds. Multiple bonds, that means either it may be double bond or it may be triple bond or functional group, functional group or substituent. Substituent compounds with the same molecular formula and differ in the position of multiple bonds or functional groups or substituents are called position isomers. Called position isomers. And the phenomenon is called position isomerism. Compounds with the same molecular formula and differ in their position of double bond or triple bond or functional group or substrate are called position isomers, and the phenomenon is called as position isomerism. Here we have one more term, that is Regiomers. We have Regiomers term. Regiomers also same thing. If there is a change in, there is a difference in the position of functional group, then we can say Regiomer. If here particularly condition, if there is a change, if there is a change in or difference, there is a change, otherwise difference in the position of functional group, particularly functional group, then we can say Regiomers. These isomers called as Regiomers. Maybe like OH group, otherwise double bond or triple bond, otherwise keto group. Like it, some examples related to Regiomers. See here, I'm giving one example with respect to position isomer, otherwise Regiomer. See here, CH2 double bond, CH, CH2, CH3 I'm writing. Otherwise, in bond line diagram, we can write like this. Here, double bond, then CH, then CH2. Like this, you can write CH2, CH, CH2, CH3. This much. This is one butene. Otherwise, but one ene we can write. But one ene. But one ene. For the same, we can write like this: CH3, CH, double bond, CH, CH3. Otherwise, we can write like this. This is but to ene. But to ene. So for the both examples, you can get same molecular formula. How many carbons? 1, 2, 3, 4. C4. And 2 plus 1, 3 plus 2, 5. 5 plus 3, 8. H8. This is the molecular formula. For both the compounds, molecular formula is same. Here also see 1, 2, 3, 4. 4 carbons are there. And 3 plus 1, 4 plus 1, 5 plus 3, 8 hydrogens are present. So these are called as position isomers, otherwise Regiomers, because here functional group, there is a change in the position of functional group, otherwise double bond or multiple bond in the sense double bond, otherwise triple bond also comes in this. Otherwise any functional group like OH. See here I am writing one more example. Here CH3, CH2, CH2, OH I am writing. This is propane one ol. Propane, write one ol. otherwise propanol. What is the molecular formula? 1, 2, 3. C3, H, here 3 plus 2, 5 plus 2, 7, and here 1 hydrogen. C3, H8O. This is the molecular formula. For the same, we can write like this: CH3, CH, here I am writing OH group, here CH3. This is propane 2-ol, propane 2-ol. Here OH group is present on first carbon, here OH group is present on second carbon. So that there is a change in the position of, there is a difference in the position of OH group. OH group is functional group, so that we can say it is region related, place related. So for the same, we can write like this: 1, 2, here CH3, CH2, then CH2, OH. This also we can write. For this, here CH3, here OH, then here CH3. CH3, CH2, sorry, CH3, CH, here OH, CH3. So ending of this line is nothing but terminal carbon. Terminal carbon always contain 3 hydrogens. Here also 3 hydrogens. Here already one OH group is there, one carbon and one hydrogen. So like this also we can write. So this is a example for Regiomers. See, for this important thing is that 2 carbons containing alcohol will not give position isomer. Similarly here for alkenes, 3 carbons containing alkene will not give any position isomer. For alkenes, minimum 4 carbons are required. Even for alkynes also, how many? 4 carbons are required. 3 carbons or 2 carbons containing alkenes or alkynes will not give position isomer. And similarly, alcohols, minimum 3 carbons are required. Minimum 3 carbons are required for giving position isomerism. Similarly, if you take ketone, here I am writing one more example related to Regiomer only. Regiomer, otherwise functional isomer, sorry, not functional, position isomer. In next session, we will discuss about functional isomerism. Here, we are discussing about position isomerism. One more example I am giving with respect to ketone. See here CH3, then here C double bond O, here CH2, CH3 if you write, 4 carbons. If you write, if you change the position of this C double bond O from here to here, then also we can get same thing. Means there is a duplicate of this. If you give numbering from this side, it is 2. It is at second carbon there is a C double bond O, so we can say it is 2 butanone. We can write like this also: CH3, CH2, C double bond O, CH3. Then we have to give numbering from this side. Then also it will take 2. That is also 2 butanone. This also 2 butanone. Both are same. Both are same. So that for ketones, even 4 carbons also you can take. It will not show position isomerism. For alcohols, minimum number of carbons are 3. For alkenes or alkynes, minimum number of carbon atoms are 4. For ketone, 4 carbons also not enough. How many carbons are required? One more carbon I am giving, I mean writing here, CH2, here CH3. This is what we can say, pentane, pentane 2-one. At second carbon, there is a ketone, one. For the same, what we can write, see here I am writing lining diagram, here like this: double bond O, CH3, C double bond O, CH2, CH2, CH3, like this also we can write. Then for the same, we can write CH3, then CH2, here C double bond O, then CH2, CH3. Otherwise, we can write CH3, then CH2, here double bond O, CH2, CH3. This is the 3 pentanone, otherwise pentane, pentane 3-one. So these two are position isomers. Otherwise, these two are Regiomers. And for ketones particularly, there also comes under metamerism. Metamerism is one of the structural isomerism only. This is related to internal functional groups. In further sessions, we will discuss about metamerism also. For ketones, particularly, these two ketones are comes under position isomer. Otherwise, one more term is Regiomer, and these are also comes under metamers. What is metamerism? What are the different examples? We will discuss in further sessions. So these are the different examples for position isomers. And with respect to substituent also we can write. With respect to substituent, substituent means it may be chloro group, it may be nitro group or amino group. We can consider any halo group also we can take. Maybe chlorine or bromine or iodine. These groups may be present on carbon chain. One more example is I am writing CH3, CH2, then CH2, X group. This is one halo. One halo. Halo maybe it is fluorine or fluoride or chloride or bromide. Halo propane. Here minimum how many carbons are required? 3 carbons are required. 2 carbons are present means it also will not give position isomerism. Because if it is 2 carbon, for example CH3, CH2, X, and if you write X here like this, both are same. This is a duplicate of this only. Here this is one carbon, this is second carbon. One halo ethane it is. If you give numbering from this side, then it is one carbon, this is second carbon. So that is also one halo ethane. So that minimum how many carbons are required? Minimum 3 carbons are required for any substance like this. This is one halopropane, CH3, CH2, then CH2X. Like this we can write. For the same we can write CH3, CH, here X I am writing, here CH3. This is like this you can write. This is CH3, CH, CH3. So it is 2 halo, 2 halo propane, 2 halo propane. This is also position isomers. But here for alkanes, only for alkanes, as to get position isomerism, minimum how many carbons are required? See here, alkane I am writing first CH3, CH3. This is ethane. Ethane will not give any position isomerism. Even propane also, CH2. Here if you write CH3, it also will not give position isomerism. Then 4 carbons also if you write CH2, CH3. For this also position isomerism is not possible. Chain isomerism may be possible like this we can write CH3, here CH, CH3, CH3 we can write like this. This 2-methyl propane. This is butane. These two are chain isomers, not position isomers. So as to get position isomer, how many carbons are required? How many carbons are required? CH3, CH2, CH2, CH3. Then here I am taking one more CH3. Even this also will not show position isomerism. See here, if you want to write like this, CH3, CH2, here or CH3 like this if you write, CH2, CH3, this much only. So here for the both the compounds we have same molecular formula. But this is butane, this is pentane. So here I am extending one more carbon here. CH3. This is hexane. For hexane, we can write like these compounds. This is the first one for hexane. Second compound I am writing CH3, CH, here CH3, CH2, CH2, then CH3 we can write. This is a hydrocarbon alkane. For a particularly alkanes I am giving. Third compound what I am writing here CH3, CH2, then here CH, here CH3. Then CH2, CH3. See 1 and 2, this combination, 1 and 2 combination or 1 and 3 combinations are chain isomers. This is N-hexane. First compound is N-hexane. Second compound is 2-methyl. 2-methyl pentane. 2-methyl pentane it is. This is 3-methyl. 3-methyl pentane. This is 3-methyl pentane. See here, second and third combination if you take. Second and third combination if you take, here this methyl group is present on second carbon. This methyl here in third compound, methyl group is present on third carbon. Both are having the same root word. That means the same parental chain, pentane. Here also pentane. But there is a change in the position of alkyl group. That is 2-methyl, here 3-methyl. So that minimum number of carbons required to show position isomerism for alkanes are 6. How many carbons are required? 6 carbons are required. That you have to remember. 6 carbons are required for showing position isomerism for alkane, only alkane. See here, like this keto group is not there. Like this halo group is not there. Like earlier examples, the OH group is not there, or multiple bonds also not present. Only alkane. Only alkane. To show position isomerism, minimum 6 carbons are required. So second and third, you can expect these two are comes under position isomers, because here methyl group is present on second carbon, here methyl group is present on third carbon. Sometimes position isomers also considered as chain isomers. Otherwise, chain isomers also considered as position isomers. I'll give one example for that here. Sometimes chain isomers also considered as position isomers. Here, I'm giving one example. Wait a minute. See, here I'm giving a 1 bromobutane. This example, observe carefully. 1 bromobutane. Here I'm writing 2 bromo, 2 methyl propane. 2 bromo, 2 methyl propane. See here, 1, 2, 3, 4. 1 bromo means here bromine I'm writing. Here butane, here H2, here also H2, H2, here H3. This is 1 bromo butane. Here propane they are asked. Here 1, 2, 3. 2 bromo. Then 2 methyl. Here CH3, here also CH3. For both the compounds, what is the molecular formula? 1, 2, 3, 4 carbons. C4. And hydrogen 3 plus 2, 5. 5 plus 2, 7. 7 plus 2, 9. H9. Then Br. This is the molecular formula for both. Here also 1, 2, 3, 4, 4 carbons, and 3 plus 3, 6 plus 3, 9 hydrogens and 1 bromine. If you observe these two compounds, here there is a butane root word, here propane root word. Based on the root word as per IUPAC nomenclature, these two are comes under chain isomers. These two are chain isomers. Similarly, you can observe here bromine is there, here also bromine is there. This bromine is present on second position, but the same bromine here present on first position. So that they are also called as position isomerism or position isomers. So they may give among the following pairs of the compounds which shows position as well as chain, otherwise chain as well as position isomerism. Like that questions they may ask. So that like these examples you have to observe. One is 1 bromobutane, other one is 2 bromo 2 methyl propane. So these are different examples. Then for aromatic compounds we have xylenes, then cresols, xylenes, cresols. Xylene means what? On benzene ring, two methyl groups must be present. Two methyl groups like this. On benzene ring, two methyl groups. So this is the 1 comma 2 dimethyl benzene. Otherwise, we can say 1 comma 2 positions are also called as the ortho positions. So we can say directly 1 comma 2 dimethyl compound, dimethyl benzenes are called as the xylenes. What are xylenes? Xylene is nothing but 1 comma 2 dimethyl benzene. 1 comma 2 dimethyl benzene. These are called as xylenes. So here 1 comma 2, not only 1 comma 2, directly what we can write here, dimethyl benzenes. Dimethyl benzenes are called as xylenes. So if you write different positions means see here I am writing methyl group here one more methyl group here. One more compound what we can write here methyl group, here methyl group. See here 1 comma 2, here 1 comma 3, this is 1 comma 4. So 1 comma 2 dimethyl benzene, 1 comma 3 dimethyl benzene, 1 comma 4 dimethyl benzene. Otherwise 1 comma 2 position is called as ortho. O xylene. Oxylene means orthoxylene. Then metoxylene. Metoxylene. This is paraxylene. Paraxylene. These three are position isomers only. There is a change in the position of alkyl groups. Similarly, we have cresols. Cresols means what? Methyl and OH, phenols. Methylic alkyl or methyl phenols. Methyl phenols are nothing but cresols. So cresols means here I am writing there is OH group, then here methyl. OH group, here methyl group. Here OH group position I am not changing. Here OH group, but here methyl group. Here OH group as it is, here methyl group. So cresols are nothing but what? Cresols are nothing but methyl phenols. Methyl phenol. Methyl phenols are nothing but cresols. So this is orthocresol. Orthocresol, and this is metocresol. This is paracresol. This is paracresol, orthocresol, metocresol, and paracresol. These three compounds you can observe they will change the position. 2-methyl phenol. This is 3-methyl phenol. This is 4-methyl phenol. All are phenols only, but there is a change in position of methyl groups on benzene ring. So that these cresols and here there are xylenes. Very many examples we can give. All they are comes under position isomers. So this is about position isomerism. First position isomerism definition you should know. Then after examples particularly. So for position isomerism we have one more name. What is the one more name? Regiomers. When we can say regiomers, if there is a change in the position of functional group like a double bond or triple bond, otherwise OH group, alcoholic group, otherwise we can say which one keto group. If there is a change in the position of these functional groups, those position isomers are also called as regiomers. Particularly for ketones, regiomer term and position isomer, and these are also otherwise considered as metamers. And particularly sometimes chain isomers may be considered as position isomers. I given one example. This one bromobutane and 2-bromo-2-methyl propane. These two are comes under chain isomers as well as position isomers. Then some more examples related to aromatic compounds, benzene ring related compounds. Here also xylenes I given one example. Cresols I given one more example. Xylenes are nothing but dimethyl benzenes. Cresols are nothing but methyl phenols. So if there is a change in the position of methyl group, then we can say position isomer. This is about position isomerism. In next sessions, we will discuss about functional isomerism. Then, if time permits, metamerism also we will discuss in next sessions. Stay home and stay safe.